Welcome to Programming in Modern C++. We are talking about a tutorial series. We are on the 4th of that series, where we are primarily trying to learn about how to build C programs. Earlier, we have understood the overall build process, particularly the GCC pipeline of build for C project. And in the last tutorial, we have learnt about the make utility, which can really make it efficient. Now, in this tutorial, we will understand the role of libraries in C. While talking about both of these languages, we are repeatedly saying we have standard library, we can use printf from stdio.h, or we can use vector from the vector component in C standard library. So, libraries are mechanisms for code reuse and to have very reliable, well tested code. So, when they are provided with the language by the compiler vendor, those are specified in the standard library, but each one of us, while building big projects, would like to build our own libraries in addition to the standard library and use them. So, in this tutorial, we intend to understand what libraries are, what does it mean when we say we have a static library or we have a shared library and so on, how to build these libraries and how to use these libraries. Right? So, this is the last of the build sequence of tutorials that is we are going to discuss on. So, what is a library? A library is a package of code that is meant for reuse by many programs. Naturally, a header is meant for reuse by multiple translation units within the same project or the same program, but libraries are a package of code which I want to use across multiple projects, right. And typically a C library will come in two pieces. One is the text part of the library, which is the header, which gives you the prototypes of functions for C, or classes and operator overloads for C++, and the other component is a precompiled binary. Now, a library is something which has been written with lot of care, well tested for a given functionality. So, you do not expect that it will change frequently. So, you do not want for every project that the library be built again. Right. So, you precompile it and keep it in the binary form, say something equivalent of .o or some equivalent of that. For example, if I work with GNU-C, I have a library called glibc, which is a binary, precompiled binary of library of C. G stands for GNU, lib stands for library, C stands for the C language. It is available on Unix. Now, some libraries may have multiple source files, multiple header files, it may have multiple binaries also. So, we will have all of them. So, they do not change. So, we do not need to recompile, and since they are already compiled objects in the machine language, they cannot be read by human beings, or even if you use a program, you will not be able to figure much out of that library. So, unless the source changes, you do not need to recreate that, and the source being opaque, it gives a good protection of your IP. If your library has an algorithm which you do not want to tell everyone, then it is all hidden in the binary code. Of course, so we will see subsequently that there has been certain philosophical drifts in this open era, And besides these binaries, people are also talking about having libraries which are open source, that is source file is available. So, there are libraries could be of multiple types. One is the static library, which is what most of the time you have been seeing. So, they are compiled and linked into the program. This is a so a static library becomes a part of your binary code, right. So, your functionality of the library becomes a part of the executable that you create. Such libraries in Unix are typically has file extension .a, in Windows they have .lib, that says these are static libraries. The other is known as dynamic library or shared library. These two words have two different meanings, but they describe the two aspects of the same type of library. Here what you have is these are routines, they are not part of your executable, they are not inside your executable, but they are outside. When you need, they will get loaded in the memory. We will show you how that structure works. So, they get available to the application at the runtime, whereas here they are available to the application in the compile time, the static, rather the linking time, right. So, it always is there. A shared object, a shared library in Unix is called shared object.so, and in Windows it is called DLL.dll or dynamic link library. There are certain variants of this which are known as import library, which can automate the process of loading and using a dynamic library. So, it is kind of a little variation of the import library. So, .so in Unix doubles as both dynamic as well as import library, whereas in Windows a small static library will be created. We will explain why we need this by the same name as the dynamic library. So, DLL needs to be there, but there may be an additional small static library which tells you what all you need to find in that library. So, this is a schematic diagram. So, I have the source files and I have the static libraries. So, what happened when I run the linker? I run the static linker, right, or I link statically, let us say. What it does? Then it takes the application file and puts the static library as a part of it, it is inside that. So, when it executes, I have the stack for my function calls, I have the heap for my dynamic allocation, and in the text segment of the memory, I have the entire application code loaded with the static library, they are all together. Now, this has a lot of advantages and disadvantages. So, application will need a recompile. This is my application source, right, and this is my static library. Obviously, if I change my application source, I will need a recompile, but here I will need a recompilation, at least a linking, even if just my static library changes, but I have not done that anything in my source code, right. It has a large footprint because you can think of stdio.h is a huge collection of functions. So, even if the linker is smart that it only picks up that part of those functions which I have actually used my code, it is a huge code, and with every application that code will get added. Right. So, at a time in the memory there may be several processes running several programs. Understandably, each one of them will have input output. If we assume that all are C programs or C++ programs, they will have input output, let us say they are C programs. So, you can think each one of that has a copy of the printf binary body, right, and all of them are. So, in the memory at the runtime there are multiple copies of these static library loaded. So, it is a waste of space, right. The footprint is large. So, particularly in small memory devices like mobile phones and so on, these become difficult. But many a times they are fast in speed at the execution, because they might take more time to load because they are bigger, but once loaded, then they may be fast because they are already in memory, which the dynamic or shared object library may not be. So, this is the view of a shared or dynamic library, where I have the source files as before, I have the dynamic libraries, I have my linker which is happening at the static time, right. But it is doing a kind of a dynamic linking. What it says that from the dynamic library, it does not include everything here. It just includes enough information so that the application program, when it needs to find a particular function, will get that information here. But the function actually is not here, it is in the dynamic library body. So, dynamic library is in terms of two components, one which has the references of where to find the function and the actual function. So, what becomes a part of the application file is not the entire code of printf, but some abstracted information which says that this is where printf can be found when I actually want to run it. So, you can see that these are independent binary components. So, when the application is loaded, this may not have been loaded. This can be loaded only when it is required. Now, if it is loaded and some other function, some other program, not function, some other program in a different process wants to also do printf, it will not need to load it again, because the printf is the same, that does not change between projects. So, it can actually load the actual binary of the dynamic library in only one copy and use it from multiple projects, which is the static cannot do. In the static library case, every executable has a copy of the total binary code of the library. Here there is only one copy. So, the single copy is a big advantage. Naturally, the added advantages are that if something has changed in the dynamic library over a period of time, something has changed here. So, you get a different code. Unlike in static library, you do not need to rebuild the system, unless of course, you make so fundamental changes that the references itself change, like whatever was printf, you decide to from tomorrow you decide to call it PPT printf, then obviously you will need to change. But if you do not do that, then you are finding out the actual binary code at the runtime. So, all that you need to do is, if you change the dynamic library, shared library, all that you need to do, you replace the original in the present one. In fact, you can have multiple versions also. Right. So, this has become very important, this has become very useful in terms of version management of applications. I mean, we all often see that our mobile phone or our laptop say that, well, I need to download this fixes. Is it downloading everything, reinstalling everything? No. What it does, it is bringing in few components where changes have been made. Now, how does it work with the rest of the system? The rest of the system already knows the references. If it were static, then you would have required to change all of your operating system code. It is not, it is just different pieces of dynamic libraries. As long as the reference to that dynamic library does not change, all that you need to do is just replace the available implementation with the new implementation. What is important is you could keep multiple copies. You say, okay, if it is before say 17th October, then you can use this copy of the dynamic library, because you have an older version, and if it is after, then you use this. So, you can automatically manage all that. So, all those putting patches to your code, regular updates and all that would have been horrendously difficult if you were working only with static libraries. So, this is very, very important for easy version management. Of course, it has a smaller footprint because most of the binary code is outside. It has a single copy, which is of advantage in the overall memory management, particularly good for small memory devices like mobile. But it may be, it depends, it may be little slow when you want to load it for the first time. You happen to load it for the first time, the load time will come in, which is not there for the static library because it is preloaded. It may be little slow because here you are not going in directly to invoke the library function, but you have to go through this reference. You will first go to the reference, find where that actual binary code is there. So, one step. So, it may be little slower, but in many cases overall it becomes much faster because much less amount of code loading in the memory is at all needed. There is a little caveat in all this is in terms of in terms of dynamic library, your function codes classes have to be reentrant. Reentrant means, because you can see that if you had two projects both having the same static library, they will have two sets of variable allocations independent. So, anything which is static in the static library, any variable that is static will be having separate copies in terms of the two projects. But here you have only one copy of the library. So, if something is static, then there is only one copy. So, if two projects are using it, one project changes and the other project will get affected. So, what you have to make sure is that you do not use that kind of static variables, and that is put in a little different way with a little bit of twist when you say that the code that you write is reentrant, which means that a function, when it is already executing in one process, can start executing in a different process. There will be no variable clash. You will have to ensure that, and if you can ensure that, then you have a reentrancy of the function, right. Not very important for your overall library understanding, but just wanted to mention this on the passing because that is a critical point. So, that is schematically what finally. So, you have a program A, you have a program B, you have static libraries, and each one of them will be statically linked into these kind of codes. If you have dynamic library, you have program A, program B, you have a one common shared library SO, which will be dynamically linked at the runtime like in here. So, a different schematic way of looking at the whole thing. So, all that we have discussed is summarized as a comparison between the static and shared library in terms of the compilation, linking time, import mechanism, size, external file exchange, file changes, time, performance, compatibility and so on. I do not want to run through each point again, we have already discussed this, it is for your summarized reference. Now, we come to the main. So, this was, I mean, though we brought in as a part of the tutorial, but this was not that much of hands on. This was to understand the concepts of libraries, particularly the difference between static and dynamic library. So, now to really get the hold, we will execute a library project. Right. So, we present a tiny project and we will build static as well as dynamic libraries for that project, with the difference that with the condition that it will use the same set of header and source files, and we will see how things work. We will later on show some Microsoft specific stuff as well. So, let us understand the project once and for all. We will not come back to this every time. So, it is a very pathological project. It has a library math.h header, which defines header of two math functions, finding max, finding mean, right, defined by me. This is a header file. So, it will have the CPP guards and all that, just for compactness I am not showing all that. Naturally, you have an implementation of this in terms of the library math.c source file. I have a print header containing a printing function, prototype of a my print function, and I have the implementation of that in the corresponding libmyprint.c. Right. So, two math functions, one printing function, two headers corresponding .c files, and using that I write my application where I include both the headers. I use the mymax function from library math.c as implemented to compute the maximum. This is to compute the minimum, and I use the myprint function in the myprint.c libmyprint.c file to print the values. Right. So, I have tried to keep the actual algorithmic functionality requirements to the simplest, so that we can focus on the real issues. Right. I mean, you can think about any big project, but this is the basic skeletal abstraction, skeletal architecture that we will always have. So, based on this, let us organize it. We have learnt from the last tutorial that code should better be organized well. So, I have my include directory having my both header files. I have my object directory of both math.o and print.o object files. I have the source directory for the header implementations, and based on that I have the application directory, which has my source, my object file, my final executable and so on. At the then I have the library directory, which includes the object and the source. So, this is the library part. So, this is the library part of the whole story. This is the application part, and this is the bridge, the header, which allows the information to be linked appropriately. So, in the library, other than the object and the source files, I have a .a file, which I would create, show how to create for the static library. Alternately, I could create a .aso for making a dynamic library. I have two make files, one for building my library, which is here, and one for building my application, which is here. Right. So, this is there is nothing sacrosanct about this. It is not that it will have to be like this, but this is just one way of doing it. Normally, when we deal with this is the part that we do not get to see. Like this part of stdio.h or math.h or iostream or vector, you do not get to see. It is all done somewhere, somehow, and all that I get to see is either this or this, and we play around only in this part. So, this is where equivalent of your stdio.h or iostream or vector. Right. So, this is, but now we are trying to not only see the use, but we want to see how to build this library. So, I have gotten into the inner details of the library structure and possibilities. So, let me first build the static library, project. So, what I do is I can build this project by putting everything together. Right, if I did not do a library, my math.c, print.c, app.c and into my app. Obviously, I do not want to do that, because neither of this should be changing usually. because these are code provided, well tested. So, every time I change my code in my application, I will still need to do a rebuild of these math.c and my print.c. Right? So, I would not like to do that, because they rarely change. So, what I will do is I will keep their dot O's already built. But then the problem is there are multiple headers, there will be a bunch of dot O's coming in. How to manage all of that? So, how do you manage when you have too many files and you want to possibly attach it to a mail or put it to a folder? What do? You bundle them together. You say we zip them together. So, we exactly do the same thing. So, what we do is we build the .o files as we have seen earlier, and then we do something like this, taking these .os. The command to do this is AR, stands for archive, which is a generic class of what we say as zip files, and we give the target name as something. Here I have given lib underscore mylib dot a. Dot a is means that it is an archive file. Right? Now, in the process of doing that, since I am not going to usually expand this, extract the individual components of dot o. I am going to do things inside that, finding out symbols and all that. So, this AR is something little different from your zip or 7z or WinRAR or stuff like that. This is a archiving utility which takes say multiple options. RCS is the very common, you can find out other options also. C tells that you create, R tells that you replace, that if something is already there you replace that, and S tells that not only you zip, but you have an index on the top. So, that I do not need to, if I want an information, I would not need to unzip the whole thing and use it. I can use the index and get to know where to find it inside the archive file. So, this is kind of is a typical process of doing AR RCS, the archive name followed by all the .os that you want to put. So, once we have bundled them together, then the way we can use it is simply in the place of where we were writing the .os here. Here we were writing these .os, right. In place of that you put the archive, because it already has both, right. And then rest of the GCC command remains same. We say -l dot means the library to be found in the current folder. We can also replace, we can instead of keeping it in my current, I can put it at a standard library path also, we will talk about that. We can put it in a default library path, and if we do that, then I can simply do -l. So, just remember what the dot a assumes is lib is a fixed starting word, followed by that is the actual name of the library. So, actual name of the library in this case is underscore mylib, and then you have dot a. So, if you want to refer to it from not by the file name, this is the file name, but by the concept that it is my mylib library, then you strip the lib part, you strip the dot a part, the name of that is L, name of that is minus the underscore mylib, and then you put L in front of that to mean that it is a library. And so, what you is saying that -l, that is what library am I going to use? -l says that I am going to use a library, what library am I going to use is. And when I say that, what it will look for? It will look for a actual file which is lib_mylib.a. Right. So, this is the basic process that you will have. Right. So, now the two make files, one for the library which we normally do not see and now we are trying to learn, and one is the application make file. Application make file is very easy to see, the typical variables as we have seen, the rule for .o, the rule for the final application building, and this is the only difference. I am saying that I will use this library from the default location. Now, to make this, to build this, I have the static library make file. This is there, AR needs to be defined because now I am going to create an archive. Then I have to make sure according to my directory structure and the application position as to where this should actually be, because INC must be available to both. Right. We can make, of course, we can make copies, but normally at least I am initially suggesting that we do not make copies, because if you make copies and happen to change one include file, it will not be reflected in the other and you will spend your entire night looking for what is the bug. Right. So, other flags and folders, these are dependency macros which expand the things which we have seen already. This is the rule to build .o files, you have seen that, and this is this is the way to build your final output. This is the .o, and here you have the archive command. So, you have $AR which is AR, you have $A flags which is RCS. So, in that process it builds. So, once you have run this make file, your static library will be built and then you can use that in your application make file to build the final application. The static library becomes a part of your application. Try this out with this example and then start building up further on the example, and if you just run that and see the execution trace, because make will keep on writing what it is doing on your console, you will be able to see that for the static library it does this, it builds the two .os and then finally archives them into the archives all of that into the .a, and the application will build the .o and then link with the .a, and then finally you execute, you will be able to see the expected result. The only thing is now the actual function implementations have all been separated into a static library with an archive. Big learning, right. What you thought is only compiler writers can do is no, you can do it so easily yourself. It is just using make in a little different way. If you go back and check on your directory folder, this is actually the dump of my directory on that date. I did it over 24th to 26th September 2021. Then you will find that these are my different app, inc and lib directories, and these are my application ones. This is my whole library stuff and so on. I would just insist, just reproduce this first in your system, so that you get confidence and then you start building with different variants of this. What happens if I have a shared, if I want to do a shared or dynamic library, right. So, this was all about static library. So, the code has the AR code to my _mylib is become a part of my final application. Now, to create a shared library or to create a .o for the shared library, object file for the shared library, this part is the same. What you specifically put as an option to GCC is -f PIC. Very commonly the community refers to it as fpic. What it means? Position independent code. So, what you are trying to say, just try to understand, when you are making a static library, you are going to put it, attach it to your application function. Main is calling my max or my mean. So, the codes are put together. So, the linker knows in the main, if it is calling my max, where it is to be found with respect to that point, absolute address. When you make dynamic, you do not have that, because that part, the actual function body of my max or my mean, will not be a part of the application. It is somewhere else, it will come in at the runtime, you do not know where it will come in. So, wherever it comes in, it has to work. So, all that you need to do is to generate a code which does not depend on the address, or rather it will depend on a relative address. That is, you are not saying that with respect to my main or call of my max in the main, this is where you can find my max. You are saying this call says that I will find it somewhere. Wherever I load, in that I have the offset to find where is my max. So, that is the basic position independent code, again a little bit of part of theory, but helps to understand. So, then you have multiple of them. So, you have dot O's which are now fpic dot O's, that is their position independent dot O's. So, you want to kind of bundle them together, archive them together. So, you do not use AR for shared library, GCC has its own option, it is called -shared. So, what you do is you take the .o files, run GCC on it, put your target as lib_mylib.so, not .a, shared object, that is just a different protocol, and you use this option -shared. So, it does the same thing, it kind of puts them, archives puts them all together, but also creates enough linking information, dynamic referencing information for you. Right? So, to use this, we will use the same SO in the final executable build, and we can similarly put .so in the default library path and use it by the same syntax of -l_mylib. These are all same and similar. The only two differences are when you first create the .o, for all those translation units which will go into the shared library, you need to do -fpic, and the other is when you bundle them together, you do not use AR command, you use GCC with -shared option, and you would be ready to go. So, in terms of the make file, they are very easy to see. Here there is hardly any difference, except this .so, this .are for my directory structure. Here you can see the differences are in terms of these. Good enough. So, now let us go ahead and complete the task. So, I will see the traces of execution. This is my build process for the library. It does the same thing with -fpic for the .o -shared, this object will get created, shared object. I use that shared object, do the same thing again to build my application. I am very excited. I want to try running it. It does not, it throws an exception, it crashes, it gives a system error. It says I cannot find, the code execution cannot proceed because lib_mylib.so was not found. Why does it say so? It says so because unlike the static library, in the static library these codes were part of myapp.exe. lib underscore mylib.a became a part of myapp.exe. Now, it is not so. Now, to be able to run, to be able to execute this, I also need this file at the runtime, because that is what the actual function codes are. So, I need to tell the system, I need to somehow communicate as to where this .so is. Otherwise, it will not be able to say that you go there and start executing the function. Right? So, that is the basic gap that happens. So, there could be some ways of handling that. One could be, a very simple way could be that I copy this lib underscore mylib.so in the application folder. The current folder, it will always look for current folder. If I copy that, simply if I copy that file and again try this, you will find that it works fine. But do not get overly excited, because certainly there will be several such .so files, and there are several projects which are using them. What would you do? You will keep on copying all .sos into all projects. That would be a mess. And again, you did shared object or dynamic library. One of the objective was to manage version, but now you are making multiple copies of that dynamic library code. Therefore, you are bringing back the version management nightmare. So, that is it is certainly not preferred at all. So, we have to find a solution to that. You can also see what the different size and all that are there. In contrast to what I had said theoretically, that static library will be bigger and dynamic library will be smaller. Here you will see that it is exactly the opposite. That is because we have very small libraries. So, naturally dynamic library or shared library has lot of index and overhead code that need to be put into that, so that it can be found at the runtime. So, that code is actually dominating, but if you see bigger libraries, then what I said earlier is actually will turn out to be correct. This is my directory listing, and what is important is this is where my .so is, and this is where my exe is, and therefore, it is not able to find it out. When I try to execute, I will have to copy it here, which is not a preferred solution. So, somehow I have to be able to tell my application that go there and you will find the .so. That is certainly the preferred option. So, that process is known as set library path. Tell the system that where you expect the library, such libraries or library binaries to be found. So, there it could be done in multiple ways. When one is both in Linux, these are certain folders in directories in Linux, which are conventionally taken to be locations of shared library. So, if you can keep it in any one of these, and the system already knows that shared libraries will have to be looked for there. On Windows, these are typically Windows System 32 or Windows folders. Okay. So, one is to place them in the defaults, other would be you can just set a path or an environmental variable. Right. There is a path variable in Windows, there is LD library path in Unix. You can just once in your system set that to a folder where you expect your .so or .dll programs binaries to be put, and they will be found in those. Alternately, there is a third mechanism that you can dynamically find and also use that at the runtime through the program. So, if you do the set path, like you can do something like this, and then you check that the path is correct. So, you have added this along with this path, you have added your own path where your library SO is there. So, if you check, you will find it there, and then your application runs fine. This will work fine, but the only catch is that this is for the particular session of your command prompt. So, you come to the next session, this disappear. So, if you want them to be persistent, you will have to go and edit the path variables, and there are different ways you can edit that in Unix as well as in Windows. Now, the third mechanism. So, one was to copy in the one was to put it in the default folders, one was to tell the system that this is the folder where you find it. The third is to find it dynamically. So, that is a very interesting. What you say is, I will in my program I will tell that this is the name of my dynamic library and ask the system to load that. Then I will tell that this is the name of my function, so that it can go into that dynamic library and find that function and returns me a function pointer. I will use it then. Very simple, 2 levels of indirection. So, you use a header dynamic library function DLFCN, which has some library functions like DL open, DL sim, DL close, like that. So, you pass the name of the standard library, name of the shared library to DL open. This is a parameter to say how to load it. Do you load it immediately or you load it when you need? So, RT lazy. So, it will be done at the implementation defined time. Then what you say is, having done this, you define a handle. Handle is a function pointer which takes nothing, gives you nothing, takes a void, returns a void. So, because you do not know what kind of function is there, so you need to assume that it is a function without any parameter and returning nothing. Right? So, then in DL sim you pass the handle in which you have opened your .so, this comes here, and specify the particular function you are looking for in your shared object, that returns you a pointer of this type. Cast it to my hello, put it to my hello, call my hello will now call this function, because it has got that handle. So, that's in abstraction the simple mechanism, and here I have given the more detailed code. Here is the inclusion, here is the library handle. So, I do a DL open of my code with RT lazy. If it is not found at that point or there is some error, then the handle will be null. I go out and give an error. Otherwise, I will use that handle to find the function by name. So, my max I specify, it returns me, DL sim returns me a pointer to that which I put to my max. So, for that these function pointers my max, my min, my print has been defined, and I get these 3 function pointers according to the relative address within my library SO, and then I dereference these functions and use them. When I am done, I close the handle. So, this is a third mechanism where I can control specifically when I want to load it, and when I close and I am done with it. So, I am not going to have it anymore. So, if you have more personalized dynamic libraries, you will be using that. So, that is an alternate mechanism, and all of these mechanisms are available both on Unix as well as on Windows. In addition, Windows have specific dynamic library DLL projects and the static library mechanisms. I will not I am not going through the details of that, because these are to be done through the Visual Studio IDE. It is a commercial one, though some academic versions are available, but in general it is a commercial one. So, we do not intend to go deep into that, but if you happen to use that, the only difference that you will see that there are certain storage class attributes called DLL specs, DLL export. So, from your dot header you are saying that I am exporting this symbol. So, I am making it available on the DLL. Similarly, when you use it, you include and use it, and you can have a DLL import on this. So, you have DLL exports and you have DLL import here to use in your application. Okay. So, this is basically what the difference in as it visualizes in the Windows. Rest of the build process can be executed through Windows Mac or through the Visual Studio IDE. So, all that I wanted to mention is there is a Windows specific process, particularly dealing with similar shared objects or dynamic libraries, which are called dynamically linked library or DLL in Windows. But certainly, if you really need to do that, you will have to look up the manual and do this. So, this brings us to the end of the tutorial series of 1 to 4, where we have taken a look at the overall build process of C, C++ project with almost the all major objectives that it wants to serve, whether what is the build pipeline, how does C preprocessor can be used to manage code, how to make build process efficient by using the make utility, how should you organize your code, and at the end how should you build your static and dynamic libraries. So, if you practice this, just listening to this is not enough, but if you practice this, if you execute those examples that I have given and also have further examples, then you will really have no difficulty with your C, C++ knowledge. You will be able to walk into your company, into your interview, and actually show them that you know how to do programming and how to manage projects. So, all the best for that. We conclude on this tutorial series. We will have some more tutorials on other aspects of programming, project and language, but that is later. Thank you very much for your attention.